Section 5.5 is on counting methods. And the significance of this section ultimately is that we're going to be able to count how many different ways something can occur. In other words, we're going to be able to count how many items would be in the sample space, for example, or how many items would be in an event, so that we can figure out probabilities without having to literally go through and list them all, particularly if it's a probability in a scenario where we can't use the addition rule or the multiplication rule. So if we can't use an addition rule or a multiplication rule, then the only way to figure out the probability is to be able to determine how many favorable outcomes there are versus how many total outcomes there are. And so we can figure that out sometimes with counting methods. So that's the purpose of section 5.5. So example, the fixed price dinner at Mabinka restaurant provides the following choices. We have a very limited menu. So for an appetizer, you have two choices. You can have soup or you can have salad. Then for an entree, you can have either baked chicken, you can have a broiled beef patty, you can have beef liver, or you can have roast beef au jus. And then for dessert, you can either have ice cream or cheesecake. Now the question is, how many different meals can be ordered? Now for this question, we are assuming that you have to order an appetizer, you have to order an entree, and you have to order a dessert. So if you're going to get one of each item, meaning one appetizer, one entree, one dessert, then how many different meals are possible? Well, one way that we can determine the number of meals possible is by creating a list. And a tree diagram can be used to help count the number of meals. So here I have a tree diagram. Now I just stole this straight out of the textbook, and I'm zooming out so you can see it all. It will fit on the screen. So what I do with the tree diagram is I look at each of the possibilities. So I have a column here, so to speak, for the appetizers, and then I have a column here for the entrees, and then I have a column here for the desserts. And so for my appetizer, I really have just the two possibilities, either soup or salad. Now, if I have soup, then I have four possibilities for entree: chicken, patty, liver, or beef. And if I have salad, I have those same four choices: chicken, patty, liver, or beef. And if I have soup and chicken, then for dessert, I have two possibilities. I could have ice cream or cheesecake. And if I have soup and patty, I have two possibilities for dessert: ice cream or cheesecake, and so on. For each one of these values here, each one of these outcomes, I have ice cream or cheesecake that I could select for dessert. So if I follow the branches, that literally lists all of the possibilities. So I could have soup, chicken, ice cream. That's one possible meal. Or I could have soup, chicken, cheesecake. That's another possible meal. Soup, patty, ice cream. Soup, patty, cheesecake. Soup, liver, ice cream. Soup, liver, cheesecake. Soup, and this is the roast beef, so soup, beef, ice cream. Soup, beef, cheesecake. So I'm just following the branches and thinking about all the possibilities. Salad, chicken, ice cream, salad, chicken, cheesecake, salad, patty, ice cream, salad, patty, cheesecake, salad, liver, ice cream, salad, liver, cheesecake, salad, beef, ice cream, salad, beef, cheesecake. So altogether, there are 16 different meals that are possible, and we've literally got them listed out here. So the answer to the question, how many different meals can be ordered? The answer is 16. Now, the trouble with the tree diagram, it works great if we have a relatively small number of possibilities. But suppose this wasn't a very limited menu like we have here. Suppose we could pick from 7 different appetizers, and suppose that we could pick from 35 different entrees, and suppose we could pick from 10 different desserts. Well, creating a tree diagram would not be very fun when there's going to be that many different possibilities. So it would be better in circumstances like what I was saying, like 7 appetizers, 35 entrees, and 10 desserts. It would be easier to figure out how many different meals are possible some other way than having to draw the tree diagram. So I want to think about that for this problem. So if you think about this, when we choose an appetizer, there's only 2 possibilities. So there's 2 choices for the appetizer. And then when we choose an entree, there are 4 choices for that. So there would be 2 times 4 different ways of choosing an appetizer and an entree. And then for choosing the dessert, there's 2 more options for that. So there would be 2 times 4 times 2 different ways of choosing 1 appetizer, 1 entree, and 1 dessert. 2 times 4 times 2 is 16. So I was able to figure out that there would be 16 meals just by multiplying instead of having to literally list them all. And so we call this the multiplication rule for counting. So if a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, R selections for the third choice, and so on, then the task of making these selections can be done in P times Q times R times so on different ways. Now again, what we're talking about here in this case is a scenario where we're completing a sequence and you've got to make a choice for each possibility. Example, a man has 3 pairs of shoes, 5 pairs of pants, 6 shirts, and 4 ties that all match. How many different outfits can the man wear? Now again, for this question, I'm assuming the man has to wear a pair of shoes, so he's going to pick 1 pair of shoes. The man has to wear a pair of pants, so he's going to pick 1 pair of pants. The man has to wear a shirt, so he's going to pick 1 of the shirts. And he has to wear a tie, so he's going to pick 1 of the ties. So it's not a scenario where, oh, maybe I'll leave the ties off, or maybe I'll go barefoot. Those aren't options. So if we're going to pick 1 of each of these, then if he picks 1 pair of shoes, well, there's 3 pairs of shoes to pick from. And if he picks 1 pair of pants, there's 5 pairs of pants to pick from. And if he picks 1 shirt, there's 6 shirts to pick from. And if he picks 1 tie, there's 4 ties to pick from. Then altogether, he has 3 times 5 times 6 times 4. That is 360. There are 360 different outfits that could be picked. This man has 360 different outfits that he could wear based on how he chooses to combine the shoes with the pants, with the shirts, with the ties. What about the next example? Changing it up just a little bit. Companies whose stocks are listed on the New York Stock Exchange have their company name represented by either 1, 2, or 3 letters, and repetition of letters is allowed. What is the maximum number of companies that can be listed on the New York Stock Exchange? So this is true. They call them their symbols, the company symbol on the New York Stock Exchange. And so again, their symbol can be represented by 1 letter, or by 2 letters, or by 3 letters. For example, F on the New York Stock Exchange, that is the symbol for Ford Motor Company. So Ford has a 1-letter symbol. MA, that's another symbol on the New York Stock Exchange. That's MasterCard. So MasterCard has a 2-letter symbol. And then a 3-letter symbol, WMT. WMT, that's Walmart. So Walmart has a 3-letter symbol that it uses for the New York Stock Exchange. So our question is, if repetition's allowed, so we could have a company, we could have A, we could have AA, and we could have AAA. If that kind of repetition is allowable, how many different companies could be listed on the New York Stock Exchange? Now, this problem's a lot like what we have up here, except we're going to have to think a little harder on this, because we're going to have to think about, well, how many different companies could be represented by one letter, how many different companies could be represented by two letters, and how many different companies could be represented by three letters. And once we know the answers to those three questions, then if we add those up, that would tell us how many companies there are altogether. So I'm going to think about one-letter companies and how many of those there are. I'm going to think about two-letter companies and how many of those there are. And I'm going to think about three-letter companies and how many of those there are. Now, if the company is going to have its symbol like Ford, one letter, how many different companies could the New York Stock Exchange have with a one-letter symbol? Well, we could have a company represented by A, that would be one. We could have a company represented by B, that's two. We could have a company represented by C, by D, by E, and so on through Z. So there would be 26 different companies that could be represented by one letter. Now, what about two letters? Well, two letters, so that could be AA, AB, AC, AD, AE, and so on to AZ. And then there could be BA, BB, BC, BD, and so on to BZ. And then there could be CA, CB, CC, CD, and so on to CZ, and so on to ZZ. Well, there could be 26 letters for the first letter, and then 26 possibilities for the second letter. So if I take 26 times 26, that's 676. There would be 676 companies that could be represented by two letters. Three letters? Well, it could be AAA, AAB, AAC, AAD, and so on. Or it could be ABA, ABB, ABC, and so on. Or it could be BAA, BAB, and so on, or BBA, BBB, and so on, and so on, and so on. So for the first letter, it could be any of the 26 letters. For the second letter, it could be any of the 26 letters. And for the third letter, it could be any of the 26 letters. So there would be 26 times 26 times 26, or 17,576 different three-letter companies. So altogether, if I take 26 plus 676 plus 17,576, that would be 18,278. So there would be 18,278 different companies that could be represented on the New York Stock Exchange. Next example. Another twist on this one. Jill has 8 songs saved on her smartphone. Jill sets the player to randomly play songs without repetition until all 8 songs have played. So once a song's played, it can't play again until all of the songs have played. How many different ways can the 8 songs be played? Well, here's how I'm going to think about that. Here's the first song, second song, third, fourth, fifth, sixth, seventh, and eighth. So when the first song plays, it could be any of the 8 songs. So for the first song, there's 8 possibilities of the song that could be played, because none of them has been played yet. Now, after that song is selected, For the second song, that first song can't play again. So for the choice of the second song, there's only 7 songs to select from. Now, when we get to the third song, these first 2 songs have already been played, so they can't play again. So for the third song, there's only 6 possible songs that could be played. And for the fourth song, there's only going to be 5 songs that could be played. And for the fifth song, there's only 4 that could be played. And for the 6th song, there's only 3 that could be played. For the 7th song, there's only 2 songs that could be played. And for the 8th and last song, there's only 1 song left. So if I take 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, that's going to tell me how many different ways that these 8 songs could possibly be played on the smartphone. Well, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, that is 40,320. So there are 40,320 different ways that these 8 songs could possibly be played using this random feature that doesn't allow the songs to repeat. Now this right here, this calculation that we just did is called a permutation. So a permutation is this kind of scenario, and the main feature of a permutation is that the order matters. So again, in this case, the order matters because if the song plays first, then it can't play second or third or so on. So the order is significant, is what I mean by that. Now, have you seen this kind of notation before? Well, that thing looks like an exclamation point, right? Well, in math, that's not really an exclamation point. In math, that symbol is called factorial. So I read this as 8 factorial. Now, 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So anytime you see a number with the factorial symbol behind it, it means you're going to take that number times the next lowest number times the next lowest number times the next lowest number all the way down to 1. So if I had 10 factorial would mean 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. If I have 3 factorial means 3 times 2 times 1. So in general, if n greater than or equal to 0 is an integer, so integer means it's a whole number, and greater than 0 means it's positive. The factorial symbol, and so in general, we're going to denote that n factorial is defined as follows. So n factorial equals n times n minus 1 times n minus 2 times n minus 3, and so on until you get to times 3 times 2 times 1. So like again, like 100 factorial. 100 factorial would mean 100 times 99 times 98 times 97, and so on until you got down to 3 times 2 times 1. Now there's 2 other parts to this definition. One of those I think is probably logical. 1 factorial is 1. So if you think about that, like 3 factorial would mean 3 times 2 times 1. 4 factorial would mean 4 times 3 times 2 times 1. 2 factorial would just mean 2 times 1. So does it seem logical that 1 factorial would just be 1? What's maybe less logical is 0 factorial. 0 factorial is also 1. Now that's not as logical, and I will explain the reason why 0 factorial is 1 in just a little bit. Essentially, it's defined that way. And it's defined that way because it has to be in order for some formulas that we're going to use to work. So it has to be 1 in order for formulas to work. And so it's been defined that way. Now, really quickly, your calculator has a factorial command on it that you can use. So if I want to calculate 8 factorial, I can type the number 8, and then I can go to the math button here, math, and then over to the probability menu. And on my calculator, it's number 4. So that is 8 factorial. So 8 factorial is the 40,320 that we calculated by multiplying it all out. Incidentally, if I do 1 factorial, it's 1. If I do 0 factorial, the calculator also knows it's 1. So the calculator can calculate factorials for us. Now, I do want to warn you, if I try to do 100 factorial on my calculator, so I go 100 factorial, I get an error on my calculator, and the error that I get is an overload error, okay? So an overload error basically means that the thing I'm trying to calculate is too big for the calculator to do. So 100 factorial is such a big number that the calculator can't calculate it. It's too big for the calculator to do. So what does that mean? Well, you can't do 100 factorial on your calculator is what that means, because it's too big of a number. But another point that I want to make that I'll point out even more later on, your calculator can handle some pretty big numbers. Like, for example, instead of 100 factorial, what if we did, say, 60 factorial? So 60 factorial, I get this, 8.3209871113 E81. What's the E81? What's that about? Well, that's scientific notation. Let me come up here so I have some place to write. So 8.3209871113 E81 really means 8.3209871113 times 10 to the 81st power. And that's scientific notation, which really means this decimal point moves to the right 81 places. So that's a really, really big number. 60 factorial is really, really huge. It's consisting of 82 digits. It's huge. So the calculator can handle that big. In fact, the calculator can handle numbers 9.9999 repeating times 10 to the 99th power. Now picture that number. 9.9999999 keeps repeating times 10 to the 99th. That would be a number that consists of 100 nines. Your calculator can handle numbers that big. A number that's made up of 100 nines. 100 factorial is bigger than that. It's hard for me to even fathom a number so big that it's made up of 100 nines. But 100 factorial is even bigger than that. So pretty big.